everybody. Welcome back. It's me, Angie, and I am here with the part 2 of the lectures. Today we're going to be going through MATH1231 and 1241, and we're going to be doing calculus today. So the 5 topics that we're going to be going through today are multivariable functions, integration, ODEs, Taylor, and applications of integration. I shall be going through the first 2, and Rashid will take over promptly afterwards. So if you have any questions, feel free to offer up in the chat, and also feel free to just raise your hand. It's not.
Your screen.
What about it?
Is on the OBS.
What? No, it's not. Oh God. Okay. Do you want me to?
Okay, let's take a peek. Sorry about more delays. Hold up. Okay. So you need to bring your stuff from the slide onto the same desktop, kind of thing.
Wait, what do you mean?
Like. Okay. That swiping thing.
This?
Yeah.
What about it?
So this is recording.
Yep. This seems fine.
Okay. But when we move over, you see
It's
how
not. Yeah.
it's
Okay,
not
I get it.
changing.
Is it because of this? No, it's not. Okay. So sorry for that. Turns out there was just a streaming difficulty, but we're back on track now, so we can get started with the first part, which is multivariable functions. Again, apologies for all the technical delays, but we will be up and running now. Okay, so the first topic, like I said, is multivariable calculus, and we're going to go through how to sort of deal with functions of several variables first. So we first came across something that's called partial differentiation at the beginning of this course. Essentially what that is in a multivariable expression, such as this one, it's got 2 variables, which are x and y. When we take the derivative, we can take it with respect to either of these two values, essentially, or these 2 pronumerals. So if we are, for example, taking the derivative with respect to x, we are going to treat y as a constant. So partial differentiation is differentiating this expression with respect to one of these variables. So like you see, we use the delta symbol to mean partial differentiation. And what this gives us is this will give us 3x squared plus y. Why is that? Because we are treating y like a constant here. So for example, if we were taking the derivative of x squared, let's say we were taking the derivative of 5x, what would we get? We would get 5, right? Similarly to how if we take the partial derivative of xy, what would we get? We would get y, because we're treating it like a constant. Similarly, if we were doing the partial derivative of f with respect to y, what we would do is we would treat x as the constant. So we would get delta f on delta y is equal to, x cubed goes to 0 because it's being treated like a constant. We would get x plus 3y squared. Okay? So all we've done is when we're partial differentiating with respect to one variable, we treat all the other variables as constants. Yeah, and those are the correct answers there. Okay? So, one thing that we explored earlier in partial differentiation was the mixed derivative theorem, and essentially what that is we have a function, f, which is of 2 variables. So let's say we can write f like f of x comma y. If f is continuous, if f is continuous, and if all of f's first and second order partial derivatives are continuous, then the order doesn't matter of the variables when we're taking partial derivatives. For example, this would have to be continuous for this rule to apply. This would also have to be continuous. This would also have to be continuous. And these 2 would also all have to be continuous. Okay? Again, these are all the first and second order partial derivatives of f. So as the condition states there, if f and all of its first and second order partial derivatives are continuous, then the order doesn't matter when we're differentiating with respect to sort of which variable. So the partial derivative, we take x first, then y first, would be the same as if we take y first, then x first. Okay? All right. So let's look at some examples of that. For example, we want to find delta x, delta y, so sort of the double partial derivative of, this function over here. Yep. So one thing that we want to notice is that this is composed of elementary functions, which means it is continuous. And we can also check that all of its first and second order partial derivatives are continuous. So as a result, that means that we can apply the mixed derivative theorem. So it doesn't matter in what order we take our partial derivatives. Okay? So as you can see here, we can apply the mixed derivative theorem. All right? And why would we want to do that? Well, one thing that you might have noticed is that if we look at this expression that's on the right, this one, it's only in terms of y, right? So this is just a function that's only in terms of y, it's got no x in it, which means if we take the derivative of that in terms of x, it would go to 0 because we're treating y like a constant. So that means it would make our lives easy. Sorry about that. It would make our lives easier if we took the partial derivative first in terms of y and then in terms of x. So let's look at that in action. If we took the partial derivative with respect to x first, we would get, what would we get? Well, we treat y squared like a variable, so, we treat y squared like a constant and x as our variable, so y squared would just be a constant, it would just kind of be stuck out the front. And when we differentiate x, we get what? We get 2x. Yeah? And that whole expression, all of which is in terms of y, we are allowed to just treat that as a constant. When we differentiate a constant, what do we get? We get 0. So all of that just goes to 0. And essentially what's going on is we want to take the derivative again. Oh, what gave it away that it's continuous? Okay, so this function is composed of elementary functions, which if you look in the Math1231 or 1141 notes, it will state that a function which is composed of elementary functions, so composed of functions that are like log, trig, polynomials, power functions, etc., and they're joined together sort of with the elementary operations of adding, subtracting, dividing, function composing, etc. You can look at the full kind of manual in the notes, in the 1141 and 1131 notes. This would mean that this function and all of its subsequent derivatives would be continuous. So we can apply that, and that would tell us that all of f and its first and second order partial derivatives are continuous. Does that make sense? That was just a question in the chat for anyone wondering. Okay, lovely. All right, moving on. So our final objective was to find this, which is also this. So we need to take the partial derivative with respect to y again. So what we want to do is we want to differentiate this thing, or take the partial derivative with respect to y. Does that make sense? Yeah, okay. So we can treat 2x here like a constant because we're taking the derivative with respect to y, so it just goes out the front. And what happens when we take the derivative of y, we get 2y. So all in all, our answer will be 4xy. Okay? And we can see that this is also what the answers say. Yeah, there we go. So this is also what the answers say. The final kind of double partial derivative will be 4xy. Okay. So moving on from the mixed derivative theorem and moving on from taking partial derivatives, let's have a look at tangent planes. So we've been sort of interpreting, these multivariable functions as, I guess, on the more kind of calculus side, so, or the more, I guess, algebraic side. So what we can do now is we can interpret them a little more geometrically. So before we think about tangent planes and before we think about normal vectors and all of that fun stuff, one thing that we need to be aware of is that an expression or a function that's in this form, P is just any multivariable function. So this is just any multivariable function. And x and y are obviously your parameters. Z is also a parameter. or a variable. If we want to sort of geometrically represent this, it would be a surface in 3D space. Okay? So it would look something like this. This is just a completely random example. Our Z would be our height. We can have Y and X here. This is just a 3D plane, so you want to imagine this in 3D space. It would just be, I don't know, like we might have some hills, for example. Just going to shade them in. I don't know, maybe we have some hills and some bumps, like this, sort of. And there's like a valley, kind of just like in there. That's one possible example of how a surface could sort of be represented. So I don't know, these are like the tops of the hills, and it's just kind of like a bumpy surface. This is one example of a surface that could be in 3D space that is represented by a multivariable function, okay? So if we want to find tangent planes to this surface that's represented by this multivariable function, what we can do is we can take a point. Let's say we're going to take this point. That point's on the surface, so it's just like, I don't know, imagine someone came along with a flag and stuck it in one of the hills. This is just a point on the surface. We can find a plane which is tangent to that surface, meaning this plane sort of intersects or briefly touches this surface at that point that is specified. Okay? So this is our point. You know, we can just call it like P0 or something like that. And we've got a plane which is tangent to our surface at the point P0. So this is what we call a tangent plane. Okay? And one thing that you might be wondering is why would normals be relevant here, and sort of what is a normal vector to a point? So a normal vector to a point is the normal vector of the tangent plane at that point, which is x0, y0, z0 in our case. Okay? So if I was to represent that geometrically on our lovely bumpy surface, we would have a vector which sort of, you know, extends past this point of intersection here. And this vector would be perpendicular to this plane. Okay? So we covered planes, we covered point normal forms of planes in 1131 and 1141. And essentially all this is telling us is that this is a vector that is perpendicular to this tangent plane. So this is what we call the normal vector at a point. Okay? And this point would be our x0, y0, z0. Right? Okay. Lovely. So, just one more thing. The kind of geometric representation of this, because it's a limited representation, it's on 2D, we want to actually imagine this tangent plane sort of extending to infinity. So it's not just like one sheet of lasagna, it goes off into infinity. Okay? So it's kind of like extending out on all these sides. It's just this one big infinite flat surface. Okay? Cool. So, what formula we've been given here is the formula to evaluate the normal vector. Okay? So here what we're doing is we're evaluating the normal vector, which is that vector that's in the bright, bold, neon pink. And there's a very specific formula that we use to evaluate this normal vector, and it is this. It's that right there. For those of you who are wondering what f sub x means, oh, my thing seems to have frozen. There we go. For those of you who are wondering what f sub x means, f sub x just means the partial derivative of f with respect to x. Okay? So this here is just the partial derivative of f with respect to y, and this here is the partial derivative of f with respect to z. Okay? And here we've got, forgot to mention this earlier, we have to put our function in the form this. Okay? So for example, if we had this, if our function was, for example, in this form, what we would have to do is we would have to move everything over to one side so we get 0 on the other side. So it would have to look like this. Oh, sorry, should be minus z equals 0. There we go. Okay, cool. So that's just one example of that. And we're able to find the normal vector using that. All clear? Okay, lovely. Let's move on. So we've talked about the normal vector. We can talk about, by extension, the tangent plane itself to the surface. And why we can do that is because for any plane, you might recall from 1131 or 1141, if we have a plane, which is just a flat surface that's in 3D space, which looks like this and it extends out into infinity, we can define this plane by two things. We define a plane by a point on the plane and a vector that is perpendicular to the plane. Okay? So a vector like this, for example, where there's like a right angle here, and a right angle here, and a right angle here, and a right angle here. Right angles everywhere, essentially. So any vector that's from this point to any point in the plane, literally any point that lies on the plane, that vector, like this one, for example, would have to be perpendicular to our normal. So just explaining the logic behind point normal form, if anything is perpendicular to another thing, so if two vectors are perpendicular, we can say that their dot product is equal to 0, right? So here, what's going on is we're taking a variable vector which we're terming x. So x here is our variable vector. If we really want, we can represent it like this. So x here is a vector, n here is also a vector, and p here is a position vector. So this x, y, z, or this variable vector, bold x, is a variable that denotes sort of any point that is on the locus of this plane, okay? So it's any point that could possibly be on this plane, because this whole thing, this whole vector that's being represented here, what does that represent? That represents, p is this, by the way, p is just any point as well, but it's fixed. Our p is fixed. Our x is variable. So this entire vector over here, what that represents is that represents these vectors, any of these vectors, any and all of these vectors for any x that is on this plane. So it would look like this. These could all be x minus p, okay? All right. And the normal is perpendicular to all of these, so their dot product will be 0. Okay. Given this, we can essentially find the tangent plane at any point. And why we can do that is because we can write our n like this. So we found this already earlier. We've sort of already talked about this earlier when we were talking about normals at points. This is the n value here. Okay, so that's just our normal vector. All right. No questions in the chat so far. Of course, feel free to raise any concerns if you would like. If not, let's go on to doing an example of tangent planes to surfaces. It might be kind of hard to visualize these actually geometrically. It might be kind of hard to actually draw them out. But what we're going to do instead is we are going to sort of just tackle these problems from a calculus / algebraically, rather than actually drawing the surfaces out and visualizing everything. So the first thing we're going to do is, just turning up the brightness. First thing we're going to do is we are going to find a normal vector to this surface. Okay, so we've got a surface that's written like that, and we've got a point which is written like this. Okay, and that is a point we've been given, that's a point that's on the surface. Okay, so what we want to do first is, if you remember earlier from when we're talking about the normal at a certain point, what we want to do is we want to, to the question in the chat, yes, this is going to be saved on YouTube if you want to watch it in the future. You can ask questions live in the chat though, so anyway. For any function that's given in this form, we can use this formula to find the normal vector at a given point P, okay? So what we want to do first is we want to actually be able to express it, or express S, in terms of f of x, y, z equals 0. So the first thing that we're going to do is move everything over to one side, so that our right-hand side is 0. Like this. So essentially this is our multivariable function that we're going to be working with. Okay, cool. So if you remember, the equation for a normal, which I'm going to denote with the vector n, is the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. Okay, so what's going on here is we just take the partial derivative. Again, when you're taking the partial derivative, you're treating all the other variables like constants. So when we're taking the partial derivative with respect to x, we're treating y and z like constants. Okay, so the diff of this with respect to x is just 3y squared. And the diff of minus z with respect to x is just 0 because it's just a constant. Let's take the derivative of this with respect to y. What would that be? That would be 6xy. And the derivative of this with respect to y would be 0 because it's a constant when we're diffing with respect to y. Okay? And the derivative with respect to z, I hope you can see, is just minus 1. So we're not quite done yet because when we want to find the normal vector, we also have to sub in our point, P. So what we have to do is we have to sub in P. We want to make this x, we want to make this y, and we want to make this z to get the actual vector. I don't have a calculator on me, but the slides do give us the final numerical value, which will be this. So we've just made this x, we've just made this y, and we've just made this z, and we've subbed them into here, okay? And that spits out our lovely actual normal vector, which is this over here, okay? So that is the vector which is normal to our tangent plane on the surface S at the point P, which is 1, 2, and 12. Okay.
So you subbed in point P into the normal, right?
Yes, so we've found an expression for the normal vector by taking the partial derivative with respect to x, y, and z. So we've used this formula, but we're not quite done yet. After we do that, we also have to sub in the numbers, the coordinates of the points to get the vector itself. Okay?
Mm-hmm.
Any other questions so far? No? Okay. Did you have a question? Okay, I'll move on. So, part B asks us to find the tangent plane of at the point. So, essentially what we need here is, by the formula, we need two things to determine any plane uniquely. We need a normal to that plane, and we need a point on that plane. We obviously already have a point on that plane. That is our lovely P. If that is the point on the surface we want to find the tangent to, it's also got to be on the tangent plane. So our P here is just 1, 2, and 12, and our N here is what we've just found in the slide above, which is 12, 12, and minus 1. So we have a point normal form for our tangent plane, which looks like this. But is that what we've been asked for? Have we been asked for a point normal form? No. We've been asked for a Cartesian form, right? So we've got to read the question to get a feel for what the question actually wants us to answer. So what is the Cartesian form of the tangent plane? Well, we want it in terms of the coordinates. Specifically, we want it in terms of x, not the vector x, just x itself. Oh, flagging. Give it a second. X, y, and z. And we can do that very easily because we know that this vector is just a variable vector, and we can actually write it in terms of x, y, and z. So what we get here is something that looks like this. Okay, so how do we then get from this to Cartesian form? What we do is we just take the dot product. Okay, so it'll look like this. I'm just going to combine them into one vector. Y minus 2, z minus 12. And when we take the dot product, what happens is we get 12x minus 1 plus 12y minus 2 minus z minus 12 equals 0. Okay? That is fundamentally our Cartesian form. It's in terms of our coordinates x, y, and z. And we can obviously do a little bit of polishing to make it look just a little bit nicer. And we will end up with an answer, which is this. Okay? So that's the final Cartesian form of our plane. All right? Okay. So, moving on from the kind of geometrical interpretation or the geometrical side of things, let's have a look at multivariable functions with approximation. So, approximating with multivariable functions. We've got a formula here, which is called total differential approximation. So if we've been given some function, which is in terms of two variables, and we want to approximate, let's say, a change in that function, let's say we know that we've just tweaked x somehow, and we've tweaked y somehow, we can estimate the overall change to the function f itself with this formula, okay? So the deltas here just mean change in, so delta f would be the overall change in f, delta x would be the change in x, delta y would be the change in y. So the formula states that the change in x is roughly equal to the partial derivative with respect to x multiplied by the change in x plus the partial derivative with respect to y multiplied by the change in y. Okay? So, and also do keep in mind that if x is a decrease, if either of these are decreases, that means that either of those variables, whichever one is relevant, is less than 0, okay? So don't be mistaken and write, I don't know, delta x is 5 when it says that delta x decreases by 5, okay? That means delta x is minus 5. All right, cool. And we can also actually get an upper bound for when we're estimating error. So when we're estimating error, we take the absolute value of our function f here, and what we do is we use the triangle inequality, we sub this in here, and then we use the triangle inequality to kind of split it up, yeah? So after splitting it up, we get something which looks like this. All right, so that's our triangle inequality, which gives us an upper bound for our absolute value of delta f. So these bars here mean absolute value. The reason that we're able to obtain this upper bound is because the triangle inequality states that a plus b is less than or equal to a plus b, with the absolute values all in place. So because that thing on the right is greater than or equal to the thing on the left, we're able to obtain an upper bound. So this is a maximum for the estimated error. Okay? Wonderful. So let's do some questions with that. Let's do this one first. The area A of a rectangle with length x and width y is A equals xy. Use the total differential approximation for A as a function of x and y to estimate the percentage increase in A when x increases by 5% and y decreases by 6%. So one common error is you don't read the question and you see increases instead of decreases. Remember, this is decreases. So this is a clear sign that your delta y will be negative, not positive, okay? So what we do after that is we want to obtain delta x and delta y. And of course, here's our lovely formula. Our multivariable function here is A. We want to find the overall change in area. So what we do is we take delta A. We use the total differential approximation formula and we get this. And now we have to find out what these two are. So what are these two? We can obviously get them from just reading the question, and what we get is that delta x is 5% of x, positive 5% of x because it's an increase, whereas delta y is negative. It is negative 6% of y because it's decreased by 6%. That's how much our y has changed. All right? So if we plug these in, we also need to obviously deal with these. What we do is we take the partial derivative of a. So a is xy. If we take the partial derivative with respect to x, we are treating y as a constant, so we just get y, which is the coefficient of x. Same with if we're taking the partial derivative with respect to y, we treat x like a constant, so our coefficient of y is just x, okay? And if we chuck all of that into our total differential approximation formula, what we should get is delta A is roughly equal to y 0.05x minus x 0.06y. Alright? If we evaluate that, we get this. Okay? So that is ultimately our change in area. And if we recall, x multiplied by, x multiplied by y is a. So the overall change in a is minus 1%. Okay? So a has decreased by minus 1% of its original, a has decreased by 1% of its original value. Yes?
Why do you keep, for the change in x and y, why do you keep the x's and the y's there?
Okay, good question. So when we say that something increases by a%, that means that the change is a% multiplied by the original value. Okay? So let's say my height has increased by 5%, right? The change in my height would be 5% times my original height before the change. So our change in x here is 5% multiplied by the original value of x before our change. So it is 0.05x. Does that make sense?
Yeah.
Lovely. Okay. So that's just a brief explanation as to why we keep x when we're writing delta x. So delta x here is not just 0.05, it's 0.05x. Because if something increases by 5%, it's increasing by sort of a metric which is measured by its original value. So we still need to keep x, the variable, there. All right? Okay. Let's move on. So we've got approximately a 1% decrease in area, and we get that from here. So when we say 1% decrease, we mean a decrease which is 1% of the original value before that decrease, which is a. All right. Any other questions? Let me check the chat. Nope. Oh. Don't think so, at least. Okay. So let's move on to chain rule. So this is quite a big part of multivariable calculus. And the chain rule is when we get, for example, a multivariable function with one of its variables in terms of t and the other one in terms of y. What we can do is we can calculate the derivative of f with respect to t. And how do we do that? We do that by taking the partial derivative of f with respect to x and then the absolute derivative with respect to t. Same with y. And the key thing here is we add them together. Okay? So this is what chain rule looks like for a multivariable function. And there is a very nice kind of graphic or a very nice kind of diagram which shows us how that goes, and it looks like this. So what this means essentially is that f is our original or our entire multivariable function. And x are the variables that f and y is directly, x and y are the variables that f is directly in terms of. And t is the variable that x and y are in terms of. Okay? So what this means is we take the product of these and we take the product of these and we add them. So we are essentially looking for all the different pathways, graphically represented, that we can get from f to t, and we're adding them. So these two things that are in the pink pathway, we multiply them. Those two things in the orange pathway, we also multiply them. And between the orange and pink pathway, we add them. So ultimately what we get is this. Added to the thing in the orange. Okay, so it's kind of like taking different routes to get to the same place. Taking different pathways to get to the same place. Okay, so it looks like that. Great, and one thing that you might have picked up on is the fact that there's delta symbols and there's also d symbols. So why is that? Well, we introduced earlier today that partial differentiation is denoted by the delta symbol. right? So f is a multivariable function, which means that when we take the derivative of f with respect to either x or y, that would be a partial derivative. So this is a partial derivative. But if we look up here, x and y are single variable functions that are in terms of t. So when we take their derivative in terms of t, we get an absolute derivative, okay? And why is it that when we take the derivative of f with respect to t that it's not partial? That's because we can write f like this, where both x of t and y of t are just functions that are solely in terms of t. So if we want to take the derivative of f with respect to t, there are no other variables that we have to consider, so this is a non-partial derivative. So that's why we denote it with a d rather than with a delta. All right, lovely. Okay, let's look at some slightly more funky chain rules. So we just dealt with one where the two variables of f are just single variable functions that are in terms of t. So if we wanted to do this, where we've got f is a multivariable function in terms of variables x and y, and x is also a multivariable function in terms of s and t, and y is also a multivariable function in terms of s and t, how would we be able to find, how would chain rules sort of apply in this situation? Again, we still can draw a diagram, right? We've got x and y here because they're the variables that f is in terms of, and we've got s and t here, which are the variables that x and y are in terms of. All right? So what's happening here is we can find the partial derivative of f with respect to s. We can also find the partial derivative of f with respect to t. F is no longer only in terms of one variable, so we're using the delta symbol here. Delta is when we take the partial derivative with respect to s and when we take it with respect to t. So it looks like this. These are two different values, okay? All right, so we're gonna do that game of kind of finding as many roots as we possibly can find now, and how we're gonna do that is we're gonna use the highlighters again. So let's look at the first one first. Let's look at delta f, delta s. What we do is we try to find as many ways as we can to get from f to s. So we've got one here, we've got one here, and that's it, right? So as I've said before, the things that are in one color, we take the product of them. So this is equal to delta f, delta x, multiplied by delta x, delta s. It's kind of a badly drawn s. And the things that are in different colors, we add them together. So we're adding this pink path and the orange path. So this would be delta f on delta y multiplied by delta y on delta s. Okay? So that's how we find the partial derivative of f with respect to s. Let's try to do that for f and t. So I'm going to pick some different colors. And just once again, we're still playing that game of finding as many pathways as we can to get from f to t. So here's one. And here is another one. Okay, colors are kind of muddled, but I hope you can see that one of the paths, the one that is in blue, is denoted by, oh Jesus, is denoted by delta f on delta x multiplied by this bit, delta x on delta t. And the bit that's in purple signifies delta f on delta y multiplied by delta y on delta t. Okay, so this is how you calculate the partial derivatives in terms for sort of slightly more complex multivariable functions that have its variables that are also multivariable functions. Okay, so playing this game of sort of finding as many paths as we can to get from the thing on the top to the thing on the bottom, that is one way that we can visualize the chain rule and derive a formula for how we can get to the expression. All right, cool. So, like I said, that's exactly how it's been expressed in the answers. And yes.
Is there a diagram of this in like the course notes or
I'm not sure. There might be, just as explanation, but this is just a method for you to visualize how we get to the chain rule, okay? All right. So let's look at another scenario where, again, our little technique of finding as many paths as we can is useful. Let's say that we have f, which is a single variable function, but this variable is a multivariable function. So, oops, apologies. So f is only in terms of u, but u is in terms of x and y. So something like this, okay? All right, so let's have a look at all the different ways that we can get from, let's first look at all the different partial derivatives, or all the derivatives that we can take. Hopefully you can understand by now that because f is a function of u, it is a multivariable function in terms of x and y. So this is multivariable, which means these derivatives are partial. Okay? So the first thing that we can do is we can find as many paths as possible to get from f to x if we want to find the partial derivative with respect to x. We've just got one. Nice and simple, we've just got one. So that's df on du multiplied by delta u on delta x. And if we want to find the partial derivative of f with respect to y, we're obviously going to be looking at how to get from f to y. And there's, again, only one way to do that, which is denoted by the blue path. Okay? So, of course, it's consistent with the answers, and this is just another way of how our technique of sort of finding a path can help us, okay? How it can help us find the chain rule for sort of multiple composite functions that are multivariable or single variable very efficiently. Okay, wonderful. We can also extend this to multivariable functions that have more than, that have 3 or more variables, so more than 2 variables. And again, you can see that we're just using this game of walking. So I'm just gonna really quickly go through this. The answers are here. So if we wanna find the derivative of f with respect to u, we look at all the different pathways that could possibly be there. So we've got one here. Oh, it's a bit thick. Make it a bit thinner. And this one is correspondent to which of these terms? Well, we've got f to x, x to s, and then s to u, so it would be this one. Okay. We've got this path as well. Okay. And which path is that? That is this path. We've got this path as well, which is which path? It is this path. We've got this path as well, which is with which path? Goes from t to u, so f to y, y to t, then t to u. That would be this one. Running out of colors now. And we've got this one as well, which is correspondent to which one? It's correspondent to, oh, hold on. The blue is just very faint. There we go, that's better. This one's correspondent to which one? It's correspondent to this one. And last but not least, this one, which is correspondent to this one. Okay, so lots of colors and a little bit confusing, but I hope you can see that just by tracing all the different ways that we can get from f to u, we can find this overall kind of chain rule expression for df on du. So let's put this to work. We've talked enough about theory. The first thing that we're going to do is we're going to try to find delta z on delta u for this function here. Okay? So the first thing that we want to do is we want to find an expression for that, and then we want to sub in values to find an actual numerical value because we've been given a specific point. Okay? The first thing we're going to do is we're going to take this and try to compose a chain rule expression for this. All right? I'm going to really quickly just draw a diagram to help us with that. Okay, and we want to get from z to u. Z to u. Okay, so here's one way we can do it. Here's another way we can do it. And here is another way that we can do it. So 3 ways that we can do it. So how we would write out this formula would be delta z on delta a times delta a on delta u plus delta z on delta b times delta b on delta u plus delta z on delta c times delta c on delta u. Okay, so that's consistent with what we've got in our answers here. Again, this is just a result of chain rule. Okay, I'm going to scroll back up here just for the formulae. So what is delta z on delta a? It's 2a. 2a because we take the derivative of a squared, and everything else is just considered a constant. What's delta a on delta u? It's 1, and we get that because we're just taking the derivative with respect to u, so that's 1. What's delta z on delta b? Delta z on delta b is the derivative of that, which is 3b squared. And what's delta b on delta u? That is 1, because we're just diffing this. Everything else in that expression is a constant to us. As you can probably tell, then we've got 4c cubed and vw, which are just treated as constants, treated as constant coefficients of u. Okay? So we've got all these things. What can we do with them? We obviously just add them up, essentially. But if we want to find the numerical values of each of these, what we want to do is we want to go through, because we've been given u, v, and w as 101. So our u, v, w is 101. We need to sub u, v, and w into our expressions for a, b, and c, so that we can get the numerical values of each of these partial derivatives. Okay? And this should be fairly intuitive, because all we're doing is we're subbing 101, 101, 101. Yeah. Okay. So, what this gives us is the partial derivative of a is 1, partial derivative of b is 1, partial derivative of c is vw. So, we can put this in here, and what we get is this. Again, we want a numerical value, so what do? We sub in our values of u, v, and w for a, b, and c. Again, and we gain this. A is 2, b is 0, c is 0. And finally, when we add all of that together, using the chain rule, our final value will be 4. Okay? Nice. Lovely. So that's how we use the chain rule, that's how the chain rule works in action, and that is the end of multivariable calculus. So, let's go through integration now. Just a quick breather, if anybody has any questions about anything we've gone through so far. Apparently not? Okay. Let's go through the final section that I will be presenting, which is integration techniques. Some of this stuff you would have seen before from high school, some of this stuff is new to you, and that's okay, we'll just be going through all of it today. So, first things first, if we have trig integrals that are in this form, there are multiple techniques that we can think of doing depending on the sign of sort of these things. So if n is odd, then we're able to do a substitution, and I'll briefly just write out how that works. Let's let n equal 2k, because n is 2k plus 1, because it's odd, and we'll get something that looks like this. What can we do here? We can change it into this, right? And then we can do a substitution. If we let u equal sine x, then du will be cos x dx. Yeah? So what that means is we can write this as u to the m 1 minus u squared to the k, forgot the k, du. And this will be a little bit easier to integrate than this big chunk of powered sines and cos, because this is just a polynomial. If m is odd, we can do something very similar. So let's let m be 2k plus 1 as well. We get sine 2k plus 1 x. Yes, of course. Here you go. If anyone wants to copy that down, now's your chance. All right, moving on. All right, cool. Moving on. So, what we can do here is we can separate out the single sign, and then we can convert the even power of the sign into causes, okay? Which will give us 1 minus sine squared x to the k, 1 minus cos squared x to the k, and cos to the n x dx. So we might be tempted, well, we will be tempted to do the substitution of u equals cosine, but we need to be careful because the diff of cosine is not sine, the diff of cosine is minus sine. So du here will be minus sine x dx. And we will get minus u to the n, 1 minus u squared to the k du. And that is, again, just a polynomial, which is easier to integrate for us than that kind of big bulk of trig expressions there. All right. Then we have the nightmare case, which is called the nightmare case because it's not as simple as the above two cases, where neither m nor n are odd and where both of them are even. So if both m and n are even, what we have are some double angle identities that we can use. If you recall, we can write cos 2x in a multitude of ways. We can write cos 2x as 2 cosine squared x minus 1, or 1 minus 2 sine squared x. And if we do some manipulation, we can tell that cosine squared can be written like this and sine squared can be written like this. What that essentially does for us is it reduces the power of the trigonometric expression. But of course, if m and n are even numbers that are much bigger than 2, then it'll be a lot harder because you'll still have to expand. There will still be more powers of cosine and sine, and there's a whole lot more manipulation. So this case is a lot more hard, but one thing that can help us out are these double angle identities here. All right? So let's go through one of these m and n are both even cases, which is sine to the 4x dx. What we can do is we can consult our double angles and put sine squared in terms of cosine 2x, which makes the problem slightly easier for us. We get something that looks like this. We chuck the 1 over 4 out the front. We expand the thing that's inside, which gives us 1 minus 2 cosine 2x plus cosine squared 2x dx. We can split this up because there are some things in here that are much easier to integrate than other things, and it'll look like this. So those first two terms should be very easy to integrate, whereas that last term is just that little bit more tricky because it's a squared power of cosine. What we do is we apply double angle again. So we've got an expression for the cosine here, but because it's cosine 2x, our double angle for cosine 2x will be cosine 4x. So we'll get something which looks like this. So what is it? It's half of 1 plus cosine double angle, which is 1/8. 1 plus cosine double angle, which is 4x here. 2 times 2x is 4x. If we integrate all of this, we'll get x on 4 minus 1 on 4 sine 2x. The integral of cos is sine, because the diff of sine is cos, and plus x on 8 plus 1 on 32 sine 4x. And let's check if that's consistent with our answers. That is consistent with our answers. So this is our final answer after we do some simplification. After we combine the like terms of the x's, this is what we get as our final answer. Okay, cool. So let's look at some other trig integrals, which we also use trig identities to help us solve. And what we're doing here is we're using the compound angle formulae. So if you might recall, here are some examples. Sine m plus nx is sine mx cos nx plus sine nx cos mx. Cosine m plus nx is cosine mx cosine nx minus sine mx sine nx. Okay, cool. If you replace n here with minus n, you can see that these signs flip for the n minus n x case. And because of these kind of identities, we can combine them and get these product to sum identities, okay? These identities are called product to sum. One common mistake when using product to sum is to forget the half out the front, so please don't do that. Always remember to put the half there. And it basically makes something which is a product of a sine and a cos, which have different coefficients of x inside, into two separate expressions of sine and cos. These two are separate. And what that means is that we can integrate them alone. There are a variety of product to sum identities that you can look up online. If you just Google product to sum, they will all be there and they will all be waiting for you. Okay, so here's the three main ones. You can take a pause and copy them down if you feel the need to. Take photos, copy them down, whatever you feel like doing. And let's have a look at how we work with them now, okay? So again, if you want to find these for further reference online, just Google product to sum formulae, okay? Cool. So let's do this one first. This one is a sine and a cos that are mixed together. So we want to scroll back up and think about which one would be appropriate for us to use. It would be this one, okay? We've got a sine and we've got a cos. So what we want to do here is we just want to plug in the formula and we'll get something which looks like this, okay? And what we can do is we can simplify this to give us half sine 5x plus sine x. All right, so something which looks like this. Finally, this is our final answer. Not our final answer, but this is our final form of the integral. And what we get is we get this as our final answer. And as always, this is an indefinite integral, so remember your plus c. Cool. So here are a couple more integrals that we can look at. This is essentially just more trigonometric identities that you need when you're doing integrals. So here are the tan sec identities. It's convenient that when you diff tan, you get sec squared, and when you diff sec, you get sec tan. So when you're working with tan and sec, you're kind of in a safe territory because you can use these important identities to help you figure out integrals that have tan and sec in them. All right, let's do some examples. Let's do this one. Okay, and I'm gonna think of a way to do this as quickly as I possibly can. And what I noticed is that the one that has a power is the sec. So I could write it like this because I want to make a sec substitution. Okay, and why can I make a sec substitution here? Because we've got sec tan out here, and when we diff sec, we get sec tan. So what that means is if we let u be sec x, du on dx will be sec tan, right? So du will be sec x tan x dx, which is conveniently what I've underlined in the pink. So this is just the integral of u cubed. So it's just u to the 4 on 4 plus c. Remember, after we integrate, we always need to convert back to our original, variable, which is x here. So we need to put it back in terms of x. And what does that give us? That gives us sec to the 4, x on 4 plus c, which is what the answers also tell us. I'm going to scroll to the final answer if you want to take a picture. Here's the final answer. Again, don't forget your plus c. This is a definite integral. This is an indefinite integral, so we need to have plus c in the expression. All right. Let's look at reduction formulae now. Reduction formula is essentially a way that we can get from a general form of an integral to something which is a little bit simpler, and we can just keep reducing down and down and down from n to n minus 1 to n minus 2, etc., 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 until we get to something very simple like, for example, I sub 0 or I sub 1 that we can very easily solve. Okay? Usually reduction formula will ask you to prove some kind of relationship, and this is the relationship that we're going to prove here. And this is going to help us with solving integrals of this kind. Okay, so let's get started. Often, you'll start with the thing that's on the left-hand side and move towards the thing that's on the right-hand side. However, here, you're starting with something which is on the right-hand side. You're starting with I sub n. And I'll explain why we do that in a second. Let me first start by saying that reduction formula and integration by parts, which you would have gone through in Math1231 or 1141, they kind of go hand in hand. Not in all cases, but in a lot of cases, we can kind of talk about how they're hand in hand essentially. So, what we've done here is we've used integration by parts. We've let our u be the whole thing inside, and we've let our v dash be 1. So our v is x, and our u dash is the derivative of that. Okay? Whatever that is. It's this. So, what we can do now is we can further simplify our expression that we've got in this line. And how we do that is we essentially actually take the derivative. So this right here is the derivative of our u. So this is our u dash. Which is this. All right? Lovely. So now what we want to do is we want to rearrange, simplify, etc., to get to something which looks exactly like that thing that we want in the answers, or in the proof. So what we do after this is we, obviously we write this in a slightly more manageable fashion. I put it in an actual fraction here. And why that's important is because here we can make the observation that will get us from this line to something which looks exactly like the thing that we're trying to prove in the question. Okay? So how do we do that? Well, this is a technique that you'll be using a lot in reduction formula. You want to observe that you can split this into two things which are denoted by I. Okay? How do you do that? You have to observe that you want to make the numerator look like the denominator. Okay, I'll say that again. You want to make the numerator look like the thing on the denominator. You want to make x squared look like 1 plus x squared. And how do you do that? You add 1 and then you subtract it. So here all we've done is we've added 1 and then we've subtracted 1. Why did we do that? So we get a 1 plus x squared out the front. And why do we want to do that? So we can simplify our expression. We can split our fraction into something which is this and something which is this. Why do we want to do that? Because that gives us two I integrals. Specifically, that gives us two integrals that look like this. Okay? So one like this and one like this. This comes from here, because we get to simplify the 1 on x squared, so it loses a power. And this one comes from here. So all we've done is we've split this expression up into two integrals, and that allows us to get to something which looks a lot like our final form. If you recall, the form that IN is in is this. So this is IN. This is IN plus 1. All right? So this is something that we can conclude here. And what's the final thing that we can conclude? This. Well, that's not the final thing yet. This is the final thing. All we've done is we've moved this over to the other side. Okay? We've moved this to the other side so that this is our subject. We've made this the subject. Because if you remember the original thing we want to prove, it's I sub n plus 1 on the left-hand side. After that, we've just divided over 2n, and we get our final answer, which is the thing that we want to prove, so we've proved it. Okay? We've proved how to get the reduction formula. All right, so let's look at some substitutions that we could do to make some integrals just a little bit more doable. The first one is this one, and it's based on the trigonometric identity sine squared plus cos squared, I'll use theta. Sine squared plus cos squared is 1, which means that 1 minus sine squared is cos squared. Okay? There's also a tan h kind of related substitution that we can make here. And essentially what that tells us is 1 minus tan h squared gives us sec h squared. Okay? So that makes it slightly more easy to deal with. For this one, we're exploiting the trig identity that 1 plus tan squared gives us sec squared. And we're exploiting the hyperbolic trig property that cos h squared minus sine h squared gives us 1, which means that 1 plus sine h squared is just cos h squared. Okay, hope we're all clear on that. One more, we're substituting a sec theta for x here with the property that, same property here actually, we've just rearranged it slightly. This property, and again, same property here, we've just rearranged it slightly. Cos h squared equals 1 plus sine h squared. Are we all clear? Okay.
What's the purpose of showing us the cos squared, sine squared equals 1, and then you can rearrange it to find cos squared theta?
It's because we have different...
Because there's a sin theta, there's not like cos squared theta.
Sorry, what do you mean by that?
I thought, like,
Oh, sorry. I've rearranged it wrong. Thank you. It should be cos... Wait, hold on. Minus 1 is sine. Yeah, there we go. Should be this.
Yeah, but
And
what's the point of like showing that? Like, how does that relate to a cos theta?
how that relates to a cos theta is I'm explaining to you why this is a substitution that we can make for x. Why is this something that would help us if we got an integral that was in this form? Okay? And why that is because if we substituted a cos theta for x here, we would be able to rewrite it as a squared. We'd be able to rewrite it as a squared cos squared theta minus a squared. Does that make sense? And we can rewrite this as a square root sine h squared, which is just a sine h, which is easier to integrate than that thing. Okay? So this is all about how we make substitutions. All right, moving on. Let's do this one. So let's use a real-time trig substitution and have a look at how we untangle this integral, or how we make life just that little simpler for ourselves. So we consult our table, thinking about what we could possibly write x squared minus 1 as. Which one of these does x squared minus 1 fall under? Falls under this one, where our a is 1. So I'm going to use a sec theta as my substitution of choice, where a is 1. So it's just sec theta. What's the diff of sec? Sec tan. Okay? Which means that our dx would be sec tan d theta. And what we get when we substitute x for sec theta is sec theta tan theta d theta over sec theta square root of sec squared theta minus 1. Oh, sorry, I've got a d theta up the top. All right. So here's where the trig identities come into play. What is sec squared theta minus 1? This is just tan squared theta, right? And what's the square root of tan squared theta? It's just tan theta. So what we get here is we get sec theta, missing a c, sec theta tan theta over sec theta tan theta d theta, which is just the integral of 1. And what is that? That gets us theta plus c. Again, remember that we can't leave it just like this. We have to write our theta in terms of the original variable. What's our original variable here? It's x, right? So let's try to find theta in terms of x so that we can, get the whole integral in terms of x, or the whole result in terms of x. Sec is 1 on cos. So this is what we get. This means that cos theta is 1 on x, and that theta is cos inverse of 1 on x. Okay? Why we need this is so that we can put this back here, because our final integral needs to be in terms of x. All right? So that's what our final integral should look like. Our final result is cos inverse 1 on x plus c. Cool. I'm going to scroll to the final answer. And that's our final answer. Okay? So feel free to take a screenshot, take photos, whatever you need. This is our final result. All right. Let's do partial fractions. So partial fractions are... Oh my gosh.
Wait, are we doing, what is it? When you have to make x equals something, is it like u substitution? So you like let x equals to this and therefore you sub it into x.
Sorry, say it again.
When you, with a trig and hyperbolic substitution, do you treat x as like u substitution? Like
Okay, in some cases,
x equals to...
when we do substitution, in some cases, it's better that we want to make it, it's better that we, let's say we've got something which looks like this, right? Something which looks like this. There's nothing that we can take as, let's say u equals something in terms of x, because there isn't like a direct kind of derivative of that ux that we can take to get something which is in our integral. So instead we let x equal something.
Oh, so, okay. So it's like similar, but instead of using u, you use x.
X is our thing inside the integral. So what we're doing is we're taking x equal sec theta here. So for every x that we see, we replace it with a sec theta. Okay?
But what with the dx? How do you get dx?
So what I did above here was if we let x equal sec theta, we can take dx on d theta. Yeah?
Oh, yeah, okay.
So we get sec theta tan theta, which means that our dx is just sec tan d theta. So we've just got dx in terms of d theta again. So our whole integral is in terms of theta, and we can just solve it.
Okay, thank you.
Okay, moving on. Let's do some partial fractions. So one thing with partial fractions is that we are trying to decompose the polynomial, which is the bottom, into irreducible real factors. Okay? Irreducible real factors. And what that means is factors that are polynomials that have real coefficients that you cannot factorize any further into other real polynomials. For example, if it was x squared minus 2 on the bottom instead of x squared plus 2, this is not irreducible because we can reduce this one. This can go further down into this. Okay? So that's the final irreducible form. But when it comes to something squared plus something positive, that is the final irreducible form. Okay? So we want to get it down into irreducible real polynomial factors. Okay? And what we do is we want to decompose this into fractions. And they've already given that to us, so that's very nice of them. The whole goal of partial fractions is to turn one big fraction into simpler fractions. So they've given this to us, so I can just apply it, and this will make integrating a whole lot easier for me. So the first thing is just a log. What is the second thing? The second thing is this. I'm going to split it up. So it looks like this. Okay, this one is chain rule, right? You can let u equal x squared plus 2, where du is equal to 2x dx. So x dx is what? X dx is half u, half du, right? So I can do that for the one in the middle. This one though, what do we do? This is a tan inverse, okay? If we recall that the dx of something over x squared plus a squared is 1 on a tan inverse x on a plus c. This is quite a familiar standard form to many of us. What we can do in the end is we can integrate everything, and it should all fall out very nicely. So the second thing is also a log. And the last thing is a tan inverse. So our A here is root 2. So it's minus 5 on root 2, tan inverse x on root 2 plus c. And this is our final integrand. Okay? So with partial fractions, the name of the game is to split this into simpler fractions. All right? Lovely. And that should be consistent with our final answer. And it is. So wonderful, we've gotten to the end of it, and that's the end of integration. So now I'm going to hand over to Rashid. He's going to be covering ordinary differential equations with you. Thanks, everyone. Thank you. Here's the mic. Here you go. Here you go.
Thank you very much.
Put a corner.
Hello everyone. Hello everyone. Thank you very much, Angie, for taking us through to part 3 of the revision seminar. So we're going to get started with ordinary differential equations, what they are and how to solve them. All right. So this is one of those topics that when you first take a look at it, when you start 1241 or 1231, it looks very scary, but the good thing about it is that once you get the hang of it, it's very formulaic. How to solve an ordinary differential equation, it just comes down to performing a set of steps. So we're going to learn those steps. All right, so these are the types of ODEs that we cover in this course. We've got separable ODEs, first order linear ODEs, exact ODEs, second order linear ODEs, and we've got 2 cases for those, homogeneous and non-homogeneous. So we'll start with the first one. Separable ODEs. These are the simplest ones. We actually did some of these in Extension 1 and Extension 2, if you remember, if you did those classes. So a separable ODE is one where both of the variables involved in the ODE can be separated fully into 2 halves of the equation. So all the x's on one side of the equal sign, all the y's on the other side of the equal sign. From here, we can simply integrate both sides. Just basically plop an integral sign on both sides of the equation and then integrate it to get your solution, to get an expression for x and y. So another way to characterize separable ODEs is differential equations where you can express it in the following form, where dy over dx is equal to some function of x over some function of y. And then obviously you can multiply through by h of y and by dx to get all the y's on the left-hand side and all the x's on the right-hand side. Okay, sometimes you'll be given a ODE that isn't separable at first glance, but sometimes you can make it separable by performing a substitution, specifically the substitution y is equal to x times v, where v is some function of x. The particular case where you can do this is when your differential equation can be expressed as dy over dx is equal to some function g of the fraction y over x, right? So that means that basically in your equation, you can group together your y's and x's into like bundles like this, right? Where the y is always in the numerator and the x is always in the denominator. So the way that we check this, right, is we see if our function satisfies this test, right? So if dy over dx can be expressed as one of these, as g, y, and x, that means that if we change if we scale y by the same amount that we scale x, right? And x, if we scale x by the same amount, so lambda, right? Then our value for dy and dx shouldn't change, because that would just mean having a lambda here and a lambda here, which would cancel out, right? So that's the test that we apply to our expression for dy and dx to see whether we can actually perform a substitution like this. So let's go through an example, see if we can do it. Here's our ODE. Let's see at first if it satisfies the test, right? Or whether we can group the x and y's into y on x. So you might actually notice that you can group it together, right? If you just divide through by x squared, as we see in the denominator of that fraction, right? It separates into a y on x and a y on x squared. That means that we can actually perform this substitution, y is equal to x times v of x. And once we do that, our expression for dy on dx becomes the derivative of xv, because that's our expression for y, which is just equal to v plus x times dv on dx, right? This is just the product rule. So v plus x on dv on dx is equal to dy on dx, right? From our substitution. And then we equate that to the right-hand side, which then becomes v plus v squared, right? And what we get is that x times dv on dx is equal to v squared. And now this is separable, right? We can separate all the v's and all the x's on separate sides of the equation and get something that's much easier to integrate. So in this case, right, we multiply through by dx, we divide through by v squared, and we divide through by x. Right, so on this side we have v squared dv is equal to x dx, 1 on x dx. Sorry, that should be a 1 on x. And then once we plot that integral sign on both sides, we can get an expression for v in terms of x, right? So once we integrate that, this is what we get. Minus 1 on v is equal to natural log of x plus some constant. And we can solve for what this should equal. So minus x on y, that's what this left-hand side becomes, is equal to natural log of x plus c. And then once we multiply through by y, we get this expression. So that's our solution. Any questions so far?
Can you explain how you integrated y x dx? Like, can you pull out this?
Oh, where is this?
It's more like the explanation. Like, what this is? I don't. Doesn't make.
Is it when you're performing a substitution?
Yeah.
Right. Okay. So so we started with this question, right?
Yeah, but then how did it break up into y over x and plus y?
Oh, right. So we just separated that into xy on x squared, right? Plus y squared on x squared. Do you see that? Yeah, we just separated the fraction, right? And then one of those, this x at the top is going to cancel with one of the x's here. So we're going to get y on x. And this is just the same as, this second term is just the same as y on x all squared. Do you see that? Yeah? And now that we've got it in this form, we know that we can perform this x times v on x substitution. Yeah?
What does it mean by x times v on x?
X times vx. So we're replacing all the y terms in our equation, right, with this new expression, right? So basically v on x, vx, sorry, is the factor by which you have to scale x to get y, right? We know that that such a function exists because if we can separate our equation into these kind of bundles of y on x, x can basically never be 0, right? And that means you can always multiply x by something to get y. And that means that such a function v on vx does exist. Does that make sense? No? It's a bit confusing, but the main thing to remember when you see something like this, right, is that once you perform this substitution, x times vx, right, you get a much more well-behaved ordinary differential equation, right? And it makes it it actually makes it separable, and that way you can integrate it and then solve for what y has to be, right? Okay. Okay, moving on. So, a step up in difficulty. First order linear ODEs. So these are of this form. So dy on dx plus some function of x times y is equal to some function of x, right? And generally, these are not going to be separable, right? And generally, you cannot express it in a way that allows you to perform the x times v on x, x times vx substitution. So we need a different technique for this one. And luckily, we have one. So let's have a look at this ODE, okay? We know that it's linear because we've got, if we divide through by this factor 2, right? Then we'll have dy on dx plus some function of x times y is equal to some function of x, in this case 3x on 2. So this is the general method to solve a first order linear ODE. If you have it in this form, then you're going to multiply both sides of the equation by a third function that's going to help you integrate. And the way you find this function is you raise e to the integral of f of x, right? So say for instance, if f of x was let's say 1 on x, right? If f of x would equal 1 on x, then integral of f of x dx we would set as the natural log of x, right? And then, therefore, our integrating factor, hx, is equal to e to the natural log of x, which is just equal to x, okay? So nice and easy in this case. Sometimes it's a little more messy, but sometimes you get a nice one like this. All right, so now you have this integrating factor hx, sorry. You multiply both sides of the equation to get this new one, right? And then because of the product rule and what you've set hx to, h of x to, you can actually rewrite this left-hand side as the derivative of the product of hx times y, all right? And the reason this is true is because if hx is equal to e times the integral of f of x dx, then the derivative of a h is going to be equal to f of x times integral of f of x dx, right? This is just chain rule, which is itself just equal to f of x times h of x, right? So what we see here is that now that we've multiplied everything by hx, right? This part here is just equivalent to the derivative of h, right? And then you can pretty easily see that this term is dy times h, and this term is dh times y, right? And that's what you get when you apply product rule. So we can reverse that and get something like this. And once we have that, that means that on the left-hand side, we've got the derivative of some function, and the right-hand side, we've just got some function of x. And from there, we can just integrate both sides to find an expression involving x and y without any derivatives. So let's do an example, okay? Let's do an example. In this case, right, first what we want to do is divide through by 2 to just kind of isolate that derivative. Right? And we identify our function f of x, right? That's the thing that y is multiplied by. This is 2x cubed. So our integrating factor h of x is equal to e to the integral of 2x cubed dx, right? Which would be e to 2 times x to the 4 on 4, which is equal to e x to the 4 on 2. Okay? So that's our integrating factor. That's the function that we multiply both sides of the equation by to get a more well-behaved differential equation. Okay? And once we do that, we're going to end up with an expression on the left-hand side that we can simplify to look like this, right? The derivative of h of x times y, right? That's on our left-hand side. And on the right-hand side, it's going to be equal to whatever we had before, which was 3 on 2x, times our integrating factor, e to the x to the 4 over 2, okay? So 3 over 2 x e x to the 4 on 2, all right? Now, we can integrate both sides and arrive at some expression with some function of x on this side, right, times y is equal to some other function of x on this side, right? And then finally, we just arrive at y by dividing through, okay? Sorry. That should be an F. There we go. Okay. I hope that makes sense to everyone, how we would arrive at the answer from there. Okay. Now, IVP stands for initial value problem, and that means that not only do we need to find a solution to the differential equation, we need to find one that actually matches the given values at the given inputs, okay? So when x equals 0, y has to equal 1. This is what it's telling us, okay? So we can see that here it's another first order linear ODE, all right? In this case, our f of x would be this, right? Being careful though, it has to be negative, right? So this is our f of x, and we would use that to calculate our integrating factor and then solve for an expression for y, okay? I'm not sure we have time to actually go through every question at this point. So this is what would happen, right? Our integrating factor is the exponential function of the integral of what we identified as f of x, right? You integrate that and you get this expression that actually simplifies quite nicely. And then when you multiply through, right, on the left-hand side, you'll get the derivative of this thing, which is our integrating factor times y, is equal to this new function of x, right? 2 on 1 minus x squared. 2 on root 1 minus x squared. And then finally, integrating from both sides, on both sides, we'll get an expression with y on this side, an expression with x on this side, and when we substitute the values that were given to us, x equals 0 and y equals 1, right? We can solve for what this coefficient of integration has to be equal to. And in this case, it's 1, right? And after that, we can happily divide through by this coefficient of y to arrive at an expression for y in terms of x. Okay. Now, something more complicated. Exact ODEs, right? So this is when you're given an ordinary differential equation that's a little more complicated than a linear first order, right? Where you have on your left-hand side a function of x and y plus another function of x and y times the derivative of y with respect to x, so dy dx, right? This is the technique that we use to solve them. We check whether this expression, this ODE, is exact, right? And the way we check that is if this function the partial derivative of this function f with respect to y is equal to the partial derivative of this function g with respect to x. And if it does, then we can define implicitly the solution through these two equations, right? Our solution, written as h of x and y is equal to some constant c, would be defined by the partial derivative of h with respect to x being f, our function from here, and the partial derivative of h with respect to y being g. So, in short, if you see a ordinary differential equation that looks like this, then you need to check whether it's exact. And if it is, then you can implicitly define the function that will be your solution and then solve for it from there. So let's try to apply this, okay?
How do you know which one should be f and which one should be g?
So this is the form, right? F is going to be the one that's not multiplied by the derivative of y, right? And g is the one that's multiplied by the derivative of y.
Okay.
Yeah, so basically to get it into this form, you group all the terms multiplied by the derivative and then factor out the derivative.
Okay.
Yeah, okay. So let's see what's happening here. We can see this is a multivariate function of y and x. This is a multivariate function of y and x, but it's multiplied by the derivative. So we can test it for being exact, right? So let's test it then. The derivative, we need to check whether it satisfies this condition, right? So whether the partial derivative of f with respect to y is equal to the partial derivative of g with respect to x, right? So in this case, f is tangent of y minus 2x. When you take the derivative of that with respect to y, the x term just vanishes. So our partial derivative would just be equal to the derivative of tangent, which is sec squared y. As for the partial derivative of g, this is our function g, x times sec squared y minus 2y. So when you find the derivative of that with respect to x, we treat all the bits with y in them just as a constant. So our derivative, our derivative is going, oh boy, okay. Our derivative of g with respect to x is just going to be the coefficient of x, which is sec squared y, which coincidentally happens to equal the partial derivative of f. So we know that this equation is exact, okay? And next, we know from that the partial derivative of our solution h with respect to x is equal to f. And what's f again? F is tangent of y minus 2x. And we know that the partial derivative of g with respect to x is equal to g. Oh, sorry. Partial derivative of h with respect to x is, sorry, I'm saying the wrong stuff. Partial derivative of h with respect to y is equal to g, and g in this case is x sec squared y minus 2y. Okay, so when we have h defined in terms of a derivative, then we just need to integrate to find it, right? So this first one implies that h of x and y is equal to this expression on the right integrated with respect to x, right? So there's just going to be an x that appears next to this tangent of y term, right? And this minus 2x is going to be integrated to become x squared. Okay, and as for this second equation that we have, that's going to apply, an important step, right? When you take the partial derivative of something with respect to x, anything with any terms with just y in them are going to vanish, right? Any functions with respect to just y are going to vanish. So our coefficient of integration in this case is not just going to be a constant, but a whole function of y, right? That we don't know what it is yet. Okay, and similarly, for the second equation that we have obtained, we know it implies that h of x and y is going to be of the form x tangent of y, integrating this part, minus y squared plus some second function of x, right? That would have vanished when you took the partial derivative with respect to y. All right, and now comparing these two equations that we've obtained, right, these two forms for h of x and y, we know that at least one of the solutions is going to be given by h of x and y, h of x and y is equal to x tangent of y minus x squared minus y squared. And we know that our solution, the form that our solution should take on, is that this function equals to some constant, right? This is the general form of the solution that we're going to get. All right, so just to recount the steps that we took, right? First, we got this ordinary differential equation. We checked whether it was exact by taking the partial derivative of f with respect to y and the partial derivative of g with respect to x and checking that they're equal, and they were. And now that they're equal, we know that we can implicitly define our solution h by saying that the partial derivative of h with respect to x is equal to f, which we have here, and the partial derivative of h with respect to y is equal to g, which we have here, okay? And then after that, we can integrate twice, first with respect to x, then with respect to y, and compare the two equations that we get to find a general solution. And this is our general solution. Okay. Moving on. So yeah, this all agrees with what the solution is showing. There we go. That's our general solution. Okay. Now, moving on to another type of ODE. This time it's second order, and that means that the highest derivative of y that we're taking is the second derivative, right? Second order homogeneous ODEs. So this is going to come in this form where the second derivative of y plus some coefficient times the derivative of y plus some coefficient times y is equal to 0. And these coefficients, you can expect them to be constants, okay? Because we don't go towards non-constant coefficients for second order ODEs in this course. And the way that we solve them is to substitute a guess that looks like an exponential function into y. And we notice that if we do that and we divide through by this common factor of a times e to the power of lambda x, right, which we know is positive, we arrive at this quadratic equation, okay? And this quadratic equation is what we need to solve to find what lambda has to be. Notice that if lambda is a solution to this quadratic equation, right, then this exponential function guess that we inserted into the ODE will have to be a solution, right, for any coefficient a. So our main task is to solve the characteristic equation that we obtained from the ODE and then use those two solutions to find the general solution to the ODE. So there's multiple cases for what we do when once we obtain the solutions to the characteristic equation, right? So as you know, quadratic equations can have one solution or two solutions or no solutions, right? No real solutions, that is. And our general solution is going to look different depending on what case is occurring, right? If the two roots are distinct and real, okay, then the general solution is going to be just the sum of these two exponential functions, where for the first one, x is multiplied by the first solution to the characteristic equation, lambda 1, and in the second one, it's multiplied by the second solution to the characteristic equation, lambda 2, okay? And that's because each of those individual terms is a solution to the differential equation, right? Because it would solve the characteristic equation. And therefore, any other solution will have to be a sum of these two given solutions. So this is what the general solution would look like. Okay, what if there's only one real root, right? If it's a repeated root, like say for instance, if the characteristic equation you obtain is some perfect square, right? Then what you do is you have that one root in both of your exponents, right? But for the second term, you multiply that exponent by an x, right? Just by that linear factor x. And that way you obtain two distinct solutions that both solve the equation, okay? And this is what your general solution would look like. Okay, and if there are two complex conjugate roots, so neither of them are real, then we have this slightly more complicated looking expression, right? Where your general solution is going to look like a exponential term with the real part of the solution in the exponent plus a sum of a cosine and a sine function in which you have the imaginary part of the solution multiplied by x. Okay? So it takes a while to derive why these are the particular solutions, why these are in particular solutions to such ODEs. But once you remember these three cases and what to do, then you'll be able to tackle basically any second order ODE. Okay. So let's have a look at this differential equation, okay? So it's second order. We've got second derivative of y plus 4 times derivative of y plus 4y is equal to 0, right? And we've got an initial value. So when x equals 0, y is also equal to 0. So let's have a look. First, we obtain the characteristic equation, right? So notice that the coefficients are just going to be equal to the coefficients of these three terms, right? 1, 4, 4, and this is what we write down. Lambda squared plus 4 lambda plus 4 is equal to 0. And we find that it's a double root of negative 2, okay? Since it's a double root, if we have a look at our table, our general solution is going to look like two exponential functions, but one of them multiplied by x, okay? So this is what our general solution is going to look like, right? All we have to do now is solve for these coefficients, right, in front of the two terms. So once we substitute in our initial values, where x equals 0 and y equals 0, we get this. We get that a has to equal to 0. And hence the general solution to this is y is equal to b times x times e to the negative 2x, okay? So any value of b that you substitute in there, any real number, that's going to yield a solution to this differential equation that we've obtained. All right, any questions so far? Okay, let's move on. Now, a little bit of a more complicated case. Up until now, we've been looking at second order equations where where on the right hand side it's all equal to 0. It's all equal to 0. Okay. But sometimes you will see a second order non-homogeneous differential equation, which means that on the right hand side you actually have some function of x, right? And you can't exactly apply the same techniques to find the solution, right? The way that we solve these ones is we find the homogeneous solution. So that's basically us pretending that it is a zero sitting here, right? And finding the solution, finding the functions of x that would solve this simplified ODE, and then finding a particular solution, so one solution that fits this differential equation. And then once we add those together, we actually obtain all the possible solutions to this whole differential equation, okay? Finding one that equals to 0 on the right-hand side and finding one that equals to f of x on the right-hand side and adding them together. So the trickiest part of this is actually finding the particular solution, yp, okay? And it's kind of a trial and error process because sometimes you make a guess and it'll be wrong and you have to update it and change it to something else, right? But once you've got the hang of it, it's pretty easy. So we've broken it down into a table for you, okay? So this breaks it down case by case, what you should guess for your particular solution, right? Depending on what the function on the right-hand side, f of x, is, okay? So if it's just a polynomial of degree n, then your guess for the particular solution should be a polynomial of degree n, right? If it's a polynomial times an exponential function, then your guess should be a polynomial times an exponential function. If it's a polynomial times some trigonometric function, then your guess should be two different polynomials, all of the same degree, one multiplied by cosine and the other one multiplied by sine. And this is the last case, if we've got all three of them, a polynomial and an exponential and a trigonometric function in there, then your guess should be basically the previous one, but also multiplied by an exponential. Okay, so let's see this applied. This is our initial value problem, okay? We've got a second order non-homogeneous ODE because we've got a function of x on the right-hand side, and we've got two initial values that our solution needs to satisfy. So let's see what we first need to do, okay? First, we pretend that this is 0, right? That on the right-hand side we have 0 to find a solution to the homogeneous case, okay? So a solution where when you plug it into the left-hand side, it yields 0. So basically we're solving this equation, this simplified equation, okay? And we know how to solve these already. You just find the characteristic equation, find your values, find your roots, which in this case are 2 and 3, right? And then get the general solution for the homogeneous case, right? So an exponential function with 2 in the exponent and an exponential function with 3 in the exponent, because those are our two roots. Okay. And we'll keep going. So to find the particular solution to the ODE, we have a exponential function, right, on the right-hand side. So to consult our table, we'll have a look. When we have an exponential function, then our guess should be an exponential function multiplied by a polynomial of the same degree, which in our case is 0, okay? So if we did try that, right, we would be trying a solution of the form yp is equal to some constant, right, times e to the 2x, right? But the problem with that is, if we substitute that particular solution into the left-hand side, right, it's actually going to yield 0 because this is just another form of the homogeneous solution we obtained, which we know yields 0. So clearly, we need to update our guess. We need to do something different, okay? And what we do, the trick that we apply whenever our particular solution doesn't work is we just multiply by x, okay? I can't really explain why we do this, but it works. And we can see that when we try this new particular solution, we can actually solve for what c has to be, okay? So if this is our yp, then the derivative of that solution would be this expression here, right? The second derivative would be this expression here. And when we substitute that in, we arrive at c having to equal -10. Okay, so we found the coefficient for our particular solution. And that means that we can find the general solution, right? We add our homogeneous, the solution to our homogeneous case with the particular solution we just found. And we arrive at this expression. The last thing we just have to do is substitute the initial values, right? The initial values in this case are that when x equals 0, y equals 1, right? So we get this equation, a plus b equals 1. And that when x equals 0, the derivative of y also equals 1. So we arrive at this expression, right? And when we solve that simultaneously, we get these two coefficients, a being -8 and b being 9. So when we just write that into where we had a and b in our general solution, this is our solution, right? This is the function that when you substitute it into this differential equation, it would equal to 10 times e to the 2x. And it would satisfy these initial values too. Okay, moving on. Now, we do still have 2 sections left to go, so it seems we're going to go quite a bit over time. This next part is on series and sequences, and our favorite, the Taylor series. There's quite a lot of content to get through, so I'm going to be going pretty quick. But if you have any questions, feel free to ask in the chat or in person. Okay, so just briefly, what is a sequence? It's pretty self-explanatory. It's an infinite sequence of numbers, right? But to be rigorous, we define it as a function with the natural numbers as its domain and the real numbers as its codomain, because for every natural number, we have a real number that corresponds to it, okay? And they're defined by a rule, sometimes explicitly, where we get a formula in terms of n, sometimes implicitly, where they're defined recursively, okay? Okay, so the main thing that we're going to be concerned about is whether or not these sequences converge or diverge, right? So it's kind of similar to what we did when we studied limits of continuous functions last term in 1131 or 1141, right? If the limit of the terms of the sequence approach some finite number, then we say that it's convergent and it converges to L. And if it doesn't, then it's divergent, right? As we go through this, the technique that we're going to be using is basically solving limits the same way that we do with functions. And the reason we can do that is that if the elements of a sequence, right, an, are defined by some function f of n, then if the limit of the function exists and is finite, then the sequence is going to have the same limit, right? And this should make sense logically, right? If we have some function that approaches some limit, and the elements of the sequence are just the values of the function at integer inputs, then it's obvious that those values have to approach the same limit too, right? Okay, so let's apply this to an example. We've got this question. We need to determine whether this sequence defined by this formula of n, whether it converges or diverges, right? The tricky part with it, the tricky thing about this one is that it is in indeterminate form. This first term would go to infinity, and the second term would go to infinity, so it's in an infinity minus infinity form. So we need to fix that up, right? Turn it into a fraction somehow. And the way we do this is by using the difference of two squares, okay? So we multiply it by the same thing except with a plus, right? And in the denominator we divide through by that thing that we multiplied, just to keep it the same, okay? And then once we expand that out via the difference of two squares formula, we're gonna get this expression here, which is much nicer. The square root disappears. And once we simplify that, right, we get a linear term. And once we divide through by the highest power of n, as we learned to do last term, we get some constant terms along with a bunch of terms that just vanish to 0. So basically, once we push that to infinity, we get 3/2 as our limit. So the sequence does converge, and it converges to 3/2. Okay. Now, combinations of sequences, right? We're going to be basically manipulating sequences to arrive at new ones. And the way that we define this is that the sum of two sequences is just the sequence that you get when you add the corresponding terms of the two sequences, right? It's pretty self-explanatory. And the same as with limits of functions from last term, right? If two sequences are convergent, then the same applies to their product and their quotient and their sum and their difference as well, right? So basically, if this limit exists and this limit exists, then the limit of the product of these two sequences is just going to equal to the limit of the first times the limit of the second, right? You can separate them out. And the same goes for the quotient and the sum and the difference. Okay, so here's a nifty little table that gives you an idea of the rate of growth for these functions, right? So what this is telling us is that these functions are ordered in increasing rate of growth, okay? So for instance, if you took the limit of an exponential function divided by a factorial function as n goes to infinity, that would go to 0 because eventually the factorial will start growing faster. And moreover, if you had the factorial on the top and this double exponent at the bottom, then as you pushed n to infinity here, that would also go to 0 because n to the n grows, would start growing much quicker as n becomes very large. Okay. Now, pinching theorem, this should be familiar from when we did it last term with continuous functions. It's pretty self-explanatory. If you have a sequence where the terms of that sequence are strictly between the terms of two other sequences, and those two sequences converge to the same limit L, then the one in the middle, Bn, has to converge to the same one as well because it has nowhere else to go, okay? And we're going to be using this theorem to evaluate the limits of some sequences. Okay, some terminology that isn't strictly required for 1, 2, 3, 1 students, but is still useful. A sequence is monotonic if it is increasing, non-decreasing, decreasing, or non-increasing for all n, right? So that means it never changes direction and it never kind of oscillates up and down, okay? A sequence is bounded above if there's some number that's larger than all the elements of the sequence. It's bounded below if there is some number that is less than all the elements of the sequence. And a theorem for you, if a sequence is a bounded monotonic sequence of real numbers, then it converges to some real number L, right? So this should make sense if you're bounded and you're increasing, right? So you're always moving towards this bound, but you can't go past it, then you're probably going to converge to some number L, right? Just to clarify though, this means that this term bounded monotonic, it specifically means bounded in the direction in which the function is changing, in which the sequence is moving. So it could be bounded above and increasing, right? Or it could be bounded below and decreasing. Oh, bounded below and decreasing. and both of these would result in the sequence converging. Okay, some more terminology. The supremum is the least upper bound, so it's an upper bound that's smaller than or equal to all the other upper bounds of that sequence, okay? And the infimum of a sequence is its greatest lower bound, right? So basically the same thing, but the opposite way, okay? And just something to note, if a sequence is bounded above, then it's always going to have a supremum. And if it's bounded below, then it's always going to have an infimum, right? This is actually a fundamental property of the real numbers, fun fact. But yeah, this is something that you can use to find the limits of these sequences. It's always going to have a least upper bound or a greatest lower bound if they're bounded. Okay, let's apply this. So we're asked to find the supremum and infimum of the following set. Now the first thing that we should notice is that we've got a quadratic at the top and a linear at the bottom, right? So it's going to be increasing. And because it's increasing, the smallest element of the sequence is going to occur when n equals 1, okay? So when n equals 1, this value of the sequence is going to equal 1 plus 1 squared over 1, which is just 2. And that's our... Sorry, did I say supremum? This is supposed to be infimum, right? Because this is the greatest lower bound, right? We're looking for the largest number that's smaller than or equal to all the elements of the sequence. And in this case, it's 2, right? Because it occurs when n equals 1. Okay, and as for the supremum, one thing we can notice is that because it's a quadratic term at the top and a linear term at the bottom, it's actually going to diverge, right? It's going to go to infinity, so it's not bounded above. And because of that, it doesn't have a supremum. The supremum does not exist. And that's our solution. Okay, now we're going to go into series. So this is basically our way of formalizing infinite sums, right, that you might have seen before, like 1 plus 1/2 plus 1/4 plus 1/8 and stuff like that, right, on to infinity. We have this idea of a partial sum, and that's the sum of a sequence, sum of the terms of a sequence up to the nth element, okay? It's notated like this, right? And if the partial sum approaches some finite limit L as n is pushed to infinity, then the infinite series is summable and converges to L, right? So basically, if the limit of this Sn term is finite as n goes to infinity, that means that whatever infinite series you're adding up, a0 plus a1 plus a2, right? It does actually converge to some finite quantity, and that is L, right? And conversely, if it does not approach any finite number, then it diverges, right? And the series is not summable. So, if a series is summable, then it's equal to just some real number, right? So we can manipulate them the same way that we do with real numbers. Specifically, if we want to add to series, a series with its terms equal to the sum of the terms of two other series is going to converge to the limit of the first series plus the limit of the second series, right? So you can just separate them out like that. And the same goes for multiplying by a constant, multiplying each term by a constant. You can just factor that out of the infinite series, and the infinite series on the left is just going to converge to that constant times whatever the original infinite series converged to. Now, something to note, the first n terms are relevant to the convergence of a sum, right? If you think about it, this should make sense. The first n terms of a series are just going to add up to some finite quantity, right? And that's not going to affect whether the series converges or doesn't converge, right? Because the sum of a finite number of numbers is never going to be infinity. So this yields that the sum of a sequence from 0 to infinity converges if and only if the sum of a sequence from n to infinity converges, right? They're the same statement. Okay, so now we're going to introduce some tests for divergence of series. Okay, first one, if the terms of the sequence that the series is adding up don't tend towards 0 as k tends to infinity, then the series diverges. Okay, and the contrapositive of that is also true. So if the series of AK converges, then that means that the terms AK have to go to 0 as k goes to infinity. Okay. Another test that we can apply is the comparison test. So when you've got a positive sequence in which the terms are strictly below the terms of another sequence, then if the second sequence, the largest sequence, converges, then the smaller one also has to converge because it has to be smaller than the larger one. And conversely, right, if the smaller one diverges, so goes to infinity, then the larger one, BK, also has to diverge because it's larger than AK. Another test that we can apply is a p-series test, right? So this applies to series of this form, where we've got 1 over k to some power, and the p-series tells us that if p is larger than 1, then it will converge, and if p is less than or equal to 1, then it'll diverge, right? And we arrive at this from something called the integral test, which we're going to go into later. But basically, we use the fact that this series behaves similarly to this integral, 1 over x to the p dx. And if you do integrate that, you'll arrive at the conclusion that p has to be larger than 1 for the integral to converge. Okay, so let's apply this. Oops. So we're given that this series, an, is a convergent series and that all the terms are positive, right? So first we have to state the limit of the sequence. Well, if the series converges, then the limit of the series, the limit of the sequence has to be 0, okay? Otherwise it wouldn't converge. So this has to be 0. Now, for the second part, use the nth test to show that this new series, natural log of an, diverges. So we need to check whether or not the terms in this sequence go to 0. Because if they don't, that means that the series will not converge, okay? And in fact, if an goes to 0, then the natural log of an, right, is going to tend towards whatever natural log of 0 is, which basically tends towards negative infinity, which means that the sequence does not actually converge, and that means that the series has to diverge too. All right, and finally, we've been given this identity, right, that x minus natural log of 1 plus x is positive for all positive x, and we have to use this to determine whether this series converges or diverges. Okay, so the first thing that we're going to do to tackle this is to rearrange the inequality. We see that x has to always be larger than the natural log of 1 plus x, which is larger than 0, okay? And because we've already defined x to be positive, we can substitute an into x, and we arrive at this inequality, right? That an is going to always be larger than the natural log of 1 plus an, which is always larger than 0. And this is just a case of the comparison test, right? We've got the terms of a sequence bounded between the terms of a larger sequence and 0, okay? And because we already know that the series of an converges, then this smaller series also has to converge. And that's the answer. Okay. Now let's apply the p-series. So we're asked to determine whether this statement is true or false. That this series is going to diverge if S is equal to 4 on 3. Okay? Well, the P series tells us that if P is larger than 1, then the series is going to converge, right? But in this case, S is larger than 1, right? So the power that we have in our denominator is larger than 1. And that means that this series does actually have to converge. And this is exactly what we have in our answers here, right? It will converge, and therefore the statement that we got is false. Okay, integral test that we mentioned earlier. So this basically is another way to determine whether a series converges or diverges, and it's by assuming that it behaves the same as an integral as n is pushed to infinity, okay? So our conditions are if the terms of our sequence ak are defined by some function f of k, which is continuous, positive, and decreasing, then we can apply the integral test, right? Basically, what this is telling us is if ak is defined by some function f of k, which is continuous, positive, and decreasing, then the series involving a of k is going to behave the same way as the integral of f of k as n goes to infinity. Okay? So basically what that means is if the integral converges, then so does the series. And if the integral diverges, then so does the series. Okay? Geometrically, this should make sense. As you should know, the integral of a function is represented by the area under its curve. Okay? So if we have something like this, this would be the area of the area under the graph of f of x, right? And the series, right, would just be equivalent to adding up the areas of the rectangles whose corners touch the graph, right, at integer inputs, right? So the area under these rectangles would be the value of the series. So in this case, you can see that because the area under the rectangles is going to be larger than the area under the graph, then if the series converges, then the integral has to converge too, right? Because it's strictly smaller than the series. But if we ignore the first term of the series, right, and we start with the second rectangle, then we end up with a set of rectangles that look like this, that lie strictly underneath the curve, right? And that means that if the integral converges, then the series has to converge too, because it's strictly underneath the graph. Okay, hopefully that makes sense. Any questions in the chat so far? No, great. Okay, another test that we use is the ratio test. Okay, so the ratio test is another test that we can employ to check whether a series diverges or converges, right? And it basically looks at the limit of the ratio between consecutive terms of the series as k goes to infinity, right? So what it tells us is that if the limit of this ratio between consecutive terms is less than 1, right, then the series is going to converge. If it's larger than 1, then the series is going to diverge. And if it's equal to 1, then you can't conclude whether it will converge or diverge from the ratio test. You have to employ a different test, okay? So the reason this is true intuitively is because if consecutive terms of the series if the ratio between consecutive terms of the series converges to some constant r as k goes to infinity, then you can basically treat the series as a geometric series. And as you know, geometric series converge only when r is less than 1. All right, hopefully that makes sense. Okay, so now let's apply this test that we just learned to check whether this series converges or diverges. So these are the terms of our sequence, and what we need to do is find the limit of the ratio between consecutive terms. So consecutive terms here would be n plus 1 squared over 2 to the n plus 1 over n squared over 2 to the n, right? And once we simplify that, we get this fraction, quadratic on the top, quadratic on the bottom, which will tend towards 1/2 as n goes to infinity, right? So the limit of the ratio between consecutive terms is less than 1, right? And that means that the series has to converge. So this converges, right? But be wary, because the ratio test doesn't actually tell us what this series will converge to, right? This doesn't mean that it will converge to 1/2. That's just the limit of the ratio between consecutive terms. All we know is that it converges to some finite number. Okay. Let's do another practice question. So here we've got a series involving terms that look like 1 over k times natural log of k squared. So what test would we employ for this one? Well, maybe you'll notice that if this were a function, then it would be pretty easy to integrate, right? Because we could do a u sub for natural log of k. So that's what we're going to do. We look at whether this integral converges or diverges, right? And when we evaluate it, we see that it does converge. And therefore, the series has to converge to. But again, be wary, because this doesn't tell us what it converges to, right? Just because the integral converges to 1 over natural log of 3 doesn't mean the series converges to the same thing. Okay. So now we're going to go into a different type of series that we haven't looked at yet, alternating series. So these are ones where the sign of the terms in the series alternates. So we have a positive followed by a negative, followed by a positive, followed by a negative, and so on and so forth, right? And we have a special test for checking whether these series converge, and it's called the Leibniz test. This Leibniz test, it says that if our alternating series meets these 3 requirements, right, then it will definitely converge. And the requirements are that the elements of the sequence, not counting the alternating signs, are all non-negative, right? That the sequence is non-increasing, right? So that no term is larger than the term before it, and that the sequence tends to 0. Okay, so if our alternating series meets all of these criteria, then we know that it will converge. Okay. So another idea that we need to cover is absolute and conditional convergence. Okay, so we say that a series is absolutely convergent if the following new series, where each term of the sequence had an absolute value applied to it, if that is convergent, then we say that the original series is absolutely convergent. And absolute convergence implies convergence. So this should make sense, because this series is going to be strictly larger than whatever the original series was. And therefore, if it converges, then the lower one has to converge too. Okay. If there are series that converge on their own, but when you apply this absolute value, they don't converge, right? And this is what we say, this is what we call a conditionally convergent series. Okay, so moving on. We're going to apply this to a question. Okay, we're going to apply this to a question. We're going to apply this to a question. Oh no, what's going on? Don't switch. Live stream, can you still hear me? All right? Okay, there's 2 people watching. I don't know. Okay, hopefully you can still hear me. Okay, so we need to determine whether this series is absolutely or conditionally convergent, or if it diverges, okay? So we can see straight away that it's a divergent series. No, sorry, not divergent series, an alternating series, right? Because we've got this -1 to the n term in the numerator. So we need to apply the Leibniz test, right, to see whether it converges. So we do see that each term, ignoring the -1 to the n, is non-negative. We also see that it is decreasing, the sequence is decreasing. And we also see that the sequence tends to 0 as n goes to infinity. So, according to the Leibniz test, the series will converge. Okay, so we know that it converges, but we don't know whether it absolutely converges or conditionally. Okay, so let's check. The way we check whether it absolutely converges is we take the absolute value of each term, right, and see whether this new series converges itself, right? And if we take the absolute value of each of these terms of the sequence, all that's going to happen is that this -1 to the n term is just going to disappear, become a 1. Okay, so we've got this new series, and we need to evaluate whether it converges or diverges. So, to evaluate whether this new series converges or diverges, we're going to apply the integral test, right? Remember, it meets our criteria because this function is decreasing, and it's continuous, and it's strictly positive, right? And when we apply this integral test, we see that the integral actually diverges. So our absolute series will also diverge. And that means that our original series, converges only conditionally and not absolutely. And that's the answer to our question. Okay. Now, Taylor series, right? This is an important part of our course. Taylor series are infinite sums used to approximate functions near x equals a. Okay, so it's just an infinite series with increasing powers of x added to the terms. Okay. If you don't want to go infinite and you only want a finite polynomial, then you can refer to it as the nth Taylor polynomial for a function near x equals a, and it's defined as just the sum of the first n terms of the Taylor series. Okay, and this is how you write it in shorthand with summation notation. Okay, something's happening. Chat, can you hear me? Is the stream working? I'm not sure if I'm supposed to switch the audio device right now. Okay, I'll say don't switch. Okay, hopefully that works. Okay, let's keep going. Oh, and a special case for the Taylor series is the Maclaurin series, where a equals 0. So it's just the Taylor series, but around x equals 0. Okay, so this Taylor series, right, it approximates a function very well around the point around which it's made, right? Around the point x equals a. It'll equal the function value at that point, and it'll agree with the function at each derivative at that point, right? But the same can't be said for the x values around that point, right? Where x doesn't equal 0. So we should be interested in how far the Taylor series deviates from the function that's trying to approximate. And this is where Taylor's theorem comes in. Okay, so it states that we can approximate a function f using a Taylor polynomial, right? So just up to n, and that the remainder, the difference between the function and the Taylor polynomial, can be written as this term r subscript n+1 of x. And we can write this remainder in 2 different forms. The first form is this complicated looking expression here, right? Where it's the n+1th derivative of our function f, evaluated at some point C, right, where C is between x and a. Oh, sorry, there should be a comma. Divided by n plus 1 factorial times x minus a times n plus 1. To the power of n plus 1, sorry. So that's one of the ways that you can express the remainder. Another way is using an integral, and this is what it looks like. If I remember it correctly, it's 1 over n factorial times the integral from a to x of the n plus 1th derivative of f evaluated at t times x minus t to the power of n dt. So these are two ways to express the remainder between a function and its Taylor polynomial. These two ways to express it are actually equivalent. You just arrive at the first one from the second one by applying the mean value theorem. Okay, and yeah, maybe you'll notice that in general, the approximation does get better as n goes to infinity, because the remainder here will go to 0 as n goes to infinity. All right, we do have some more slides to go through and a whole other section actually, but we've already run so far over time that we might cover them a different time. So if you have any questions, right, feel free to pop them in the chat, or if you're watching later, feel free to pop them in the MathSoc Discord. We've always got lots of people willing to help you with whatever questions you may have. All right, thank you for joining us, and we hope to see you at the next revision seminar, which is on Thursday. Thank you. Wait, which one? Oh no.
This is how it's gonna go.
Yeah.
You're gonna record the rest of this video. I'm gonna record the one for the next section. Got it?